Okay, so here's the video for section 3.6, perpendiculars and distance. This section is a pretty big section on kind of some visual stuff and kind of some general things we maybe take for granted in daily life, but this is kind of getting back to some maybe more, even though it's weird, abstract, kind of practical geometry as well. So first of all, we have talked about lines being parallel, and now we're going to talk about distance between a line and a point and distance between parallel lines. So first of all, distance between a point and a line. Okay, the distance between a point and a line, not on the line, okay, is the length of the segment perpendicular to the line from that point. Okay, right. Now to kind of let that sink in, I'll go to a drawing here. They've got in this problem here, they've got all kinds of distances between this point C that's not on the line and then the line AB. Now, the thing is, you could count all kinds of different distances that you could go with. So we need to be consistent when we say, what do we mean by distance? Well, it was decided that it would be the perpendicular distance, and that wasn't done arbitrarily. That's because this is also the shortest distance. So we'll just say, yeah, the distance is the shortest distance. Like, for instance, if you had to run to the wall for some reason, you're playing tag, and the wall is home base, you wouldn't go, unless there's like if someone's coming from over here, you would go right to this perpendicular distance to be the shortest distance you could be. Okay. So that's why we use that as that distance. Now the next, the perpendicular postulate. We've already talked about the parallel postulate. Well, the book brings up in this section the perpendicular postulate. And this works in a very similar manner. And the perpendicular postulate just basically says if given a line and a point not on the line, there exists exactly one line through the point that is perpendicular to the given line. Now that last definition and this postulate work together for a reason, and again I'll go to another slide to show you that. So first of all, if I just make up some line, I'm just going to make it up myself. I've got this above me, but just say I make up a line. Okay, and here's a point not on it. Call that point A. All right, now we already established that if we're going to talk about the distance, it's going to be the perpendicular distance. But this one says the other thing that's important about this to know is there's only one perpendicular line. And I'm just sketching this in class. Actually, I'll show you how to make this perpendicular line, but right now I'm just sketching it. And if I just sketch it, there's only one perpendicular line, because if I form another one, it would just be on top of itself. And that's important for us for two reasons. One is it means that this line isn't curved. I keep running spacing. It means that either this line nor this line, neither of them are curved. But what it also means that's important is there's only one shortest distance. There aren't two shortest ways to get there. Okay, and that goes back to that previous one. That one, the distance between a point and a line is the shortest distance that's perpendicular. And this postulate says, yes, there's only one perpendicular line, so it means there's only one shortest distance. So there's not, like if I wanted to make a shortest path here, I couldn't have two ways. It'd just be, nope, the one way that's perpendicular to it will be the shortest distance to it. Okay, so let that sink in for a second. All right, next example then. Okay, again, a lot of the examples here are kind of short, so to speak, but it says which segment represents the shortest distance between point A to DB. Okay, so if I go to the drawing, whoops, wrong picture. Which segment represents the shortest distance from A to DB? Well, we're talking about a kite, and one of the things you need to know about a kite, and we'll learn this later on for sure, is that when you have the segments that make up the diagonals of the kite, this is the wooden part of it or plastic, whatever it is that gives it the shape of a kite, it's perpendicular. When they say which segment is the shortest segment, well, if it goes from A to DB, it has to be the one that's perpendicular there. Hey, it's AX. That's the shortest distance. Okay. Whatever that segment length is, that's going to be the shortest way to get there. Anything else will be a little longer. Now the rest of this section then really is again some theory stuff. So first of all, distance between parallel lines. Okay. The distance between two parallel lines is the perpendicular distance between one of the lines and any point on the other line. Now, here's what that means. I'm going to draw two lines that are parallel as best I can, freehand. Okay, yeah, I didn't do too bad. So if I want to know how far apart are those two lines, what I do is I connect them with the segment that's perpendicular to both of them, and that distance is the distance of how far apart they are. So if that's 5, then they're 5. I don't go diagonally and let it be kind of a weird, like maybe 7 where it'd be a little longer. No. The distance is the perpendicular distance for a line that's perpendicular to both. And then theorem 3.9 says, okay, fine, in a plane, if two lines are equidistant from a third line, then the two lines are parallel to each other. So here's what I'm going to start with. Here's the first line. And let's say that line, so this is line 1, or this is the third line actually. Let's say the first line here is 5 away from this line. If you're 5 away the opposite direction all the time, hopefully you can see these two lines are parallel to each other, and in fact they're also parallel to the third line. Okay. Now that also leads us to our other two theorems that the book doesn't include, but I put into this section as a teacher. First of all, this is from an old textbook, but I think this is a good theorem to know. If two lines are parallel to the same line, then they have to be parallel to each other. Okay, and that goes back to this theorem here, really. Kind of, the book skips this. They kind of cover it, but they don't. They hide it in this. They're saying if you're equidistant, if they're both equidistant from the same line, they have to be parallel to each other. Well, I'm going to say a little bit step further. Hey, let's say we knew that these two lines were parallel to this line, because that's how they'd be equidistant from it. They'd also have to be parallel to each other. Now, what if this one's farther away, though, the whole time? That's fine. If this is 7 away and this is only 5 away the whole time, they're still all three parallel to each other. So that's that first one. Okay, so I'll leave it here for a second. You'll probably need to pause the video. But if two lines are parallel to the same line, then they are parallel to each other. Now, the next one states if two lines are perpendicular to the same line, then they are parallel to each other. We've already covered this in one form, but now I'm kind of covering it in a different form. It was if two lines are parallel and perpendicular to one line, they're perpendicular to the other. We're flipping this. It's like the converse of that theorem. So if two lines are perpendicular to the same line, then they're parallel to each other. So that's what we're using. Okay. So, and again, it works because we have corresponding angles that are congruent. So the corresponding angles mean the lines are parallel then. So here's our first example, or your two examples for homework, I should say. How you're going to show that A is parallel to B. So first of all, for example A, explain how you'd show that A is parallel to B. Say any theorems or postulates you'd use, so that's problem 1. And then problem B, explain how you would show that A is parallel to B, and say any theorems or postulates you would use for that one. Okay. B has a little bit more work to it for you to do, but route your explanation. So there's your homework for the night. Is just how do you know that A and B are parallel in example A? How do you know that A and B are parallel in example B?